time. We can start. Just let me scroll this. Okay, so on the last lecture, we have introduced the concept of entropy as a measure of quantity of information. So how to objectively measure the information content using the entropy. And this entropy is nothing else but like average measure of surprise. So we have some symbols. These symbols are generated using this generator. The symbols are drawn from a finite alphabet. In this example here, we have a finite alphabet of n possible symbols, and then we simply generate a sequence of such symbols, S2, S7, S1, blah, blah, blah. And each of these symbols has its own probability. This pi is the probability of observing symbol I. P1 for S1, P2 for S2, up to Pn for symbol Sn. And this probability doesn't have to be equal for all of these symbols. Some symbols are more oftenly observed, some more seldomly. For that reason, the conventional binary code to encode these symbols is not the best solution if the probabilities are different. And then, ideally, I would like to have the code word that has variable length. If the symbol is less probable, if the probability is lower, then for such symbol, I should use a longer word. If some symbol is quite oftenly observed at the output of the generator, then such symbol should have as short as possible word length. And this concept of variable word length encoding was introduced by this guy here. So one of such codes, one of such variable word length codes was introduced by David Huffman. He was born in 1925 in the last century, and he was a mathematician, and as a hobby, he had a hobby of folding paper in 3D shapes. So it is just a paper, and he would fold this paper into some nice 3D shapes. Okay, and what he proposed? He proposed that exactly as we said, if we have several symbols that have different probability of observation, then normal good idea would be to assign shorter code words for more probable symbols, and of course longer code words for those that are seldomly observed at the output of the generator. But to have such a variable word for each of the symbols, there is one prerequisite that must be met. Otherwise, I cannot decode the sequence. And this prerequisite is that this code must be prefix code. And that means that none of the words must be beginning of some other word. So the beginning of the word must be unique. And I will explain this on an example, and it will be immediately clear why is this requirement. Such codes that fulfill this requirement are called prefix codes. Okay, the algorithm to construct the coding table is described with this diagram of algorithm, or let me try to explain this on the actual example. Suppose that we have a generator that generates 4 different symbols. So the dictionary is only 4 symbols, A, B, C, and D. And the probability of these symbols is, of course, not equal, but this symbol B occurs in 1/2 of the samples. So each second in average symbol is symbol B. The probability of symbol C is 1/4. So each fourth symbol in average is the symbol C. And finally, A and D, they have probability of 1/8, 1/8. And then this algorithm, how to construct Huffman coding table, I will explain it for this example in a very simple way. So first you start from this list of probabilities, and you search for two symbols with the least probability, with the lowest probability. In our example, that would be symbols A and D. They have the lowest probability of all of the symbols. And what I do, I simply, so I have this A, B, C, and D. And so this is 1/8, this is 1/2, this is 1/4, and 1/8. So I go to this list, and I find two symbols that have the least probability of observation. And I combine these two into like a sub-branch. So I have sub-branch that branches into A and D. And then I will assign the probability of observing A or D. This probability is 1/4 because it is 1/8 plus 1/8. Now I have three symbols. And first symbol is, let's say, AD symbol. And I have B symbol and C symbol. Now I again scan through all of these symbols, and I try to find which two have the least probability of observation. This is 1/4, this is 1/4, okay? So I combine these two into another sub-branch, okay? So the output of this one is combined with this one. And then I have this combined symbol AD, ACD. And finally, I have here symbol B. This one has probability 1/2, and this one as well. So I finally combine these two, and I finally have the root of this coding table, and this root has the probability of 1. Now I have the tree, the coding tree. And what I have to assign, I have to assign actual binary codes to each of these branches. And I start from the root, and I say, okay, I assign 1 here, 0 here. Then I have another branching here. Just check, let me check if it is correctly assigned. B would be 1. No, so that's what it. So in this case, just to be the same as on the slide, B would be 1 and ACD would be 0. Then again, on this next branching, I would assign 1 to C. So this C would have code 1, and this AD would have code 0. And finally, the last branching is D would be assigned binary code 1 and A 0. Now, in order to construct the coding table, I just simply go along these branches. And I read that, okay, for symbol B, I have only 1 bit code, and that is 1. Then for symbol C, it must be first 0 and then 1. So I go up a branch here, 0, and then down 1. For symbol whatever, D would be, so I start again the same as C, 0, but not 1, but 0, 0, 0, 0, 0, 0. And then if I want to end up with a leaf, this is like a leaf on the tree, this D is then 1. And finally, the symbol A is 0, 0, 0. So A is 0, 0, 0, B is 1, C is 0, 1, and D is 0, 0, 1. Okay. This encoding would hopefully have a lower average bit rate for transmitting symbols that have such statistics than a binary code, 2-bit binary code. And we will check whether that is true. Finally, just to emphasize the fact, this can be also 1 and this can be 0. So there isn't any special rule where I would assign 1 to one of the branches or 0 to another branch, or the other way around. So it is only the convention, the question of convention, which code I would assign to upper or lower branch. So for example, the upper branch would have 0 code, the lower branch would have 1 code. But it is only the issue of convention, because the actual coding might be that I assign 0 to the symbol B, and then all of those codes start from 1 something. And as you will see, this B, that is code 1, this 1-bit long code is never observed as a prefix in neither of those remaining symbols. So all of the remaining symbols must start from 0, because this 1 means it is B, and B is encoded with a single bit. If this bit is 1, then it is symbol B. So all of other codes must start from 0, from bit 0. Again, this 0, 1 is unique for symbol C. So neither D or A should start with 0, 1. So they start with 0, 0, because this prefix 0, 1 is reserved for symbol C. So D and A must start with 0, 0 something, 1 or 0. And that is the fact that these codes are called prefix codes. Because if certain code is, for example, value 1, none of the other codes should have 1 at the beginning. It must be 0 something, okay? And now we will check what is the average word or bit, what is the average bit rate required to transmit such set of symbols, okay? To have this average bit rate, I have to multiply the word length with probability. So I have to find what is the average bit rate, because probability of A is 1 over 8. And what is the word length for A? Word length of A is 3 bits. 3 bits. For B, the probability is 1/2, and the word length is 1. Only single bit is used to encode symbol B. For C, probability of C is 1/4, and the word length for C is 3 bits, or what? No, 2 bits. 2 bits. And finally, probability for D is again 1 over 8, and word length of D is 3 bits. Now I have to multiply the probability with the word length to get the average word length. So this average word length would be sum of pi multiplied by word length of symbol I. Symbol I. Symbol I. Okay? And in our example, this is 1 over 8 times 3 plus 1 over 8 times 3 plus what I have, 1/2 times 1 plus, sorry, and plus 1/4 times 2. Okay, and that is altogether 6 times over A, or 3 times over 4, these two. 3 times over 4, plus this is 1/2, and this is 1/2. And altogether it is 7 over 4, or 1.75 bits per symbol. So the average bit rate required to encode one symbol is 1.75 bits per symbol. Okay? It says here, so the probability of symbol A, that is 3 bits long, plus probability of symbol D, again 3 bits long, blah, 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 1.75. And if I would compute the entropy in this case, I might ask myself, what is the entropy? According to this definition of entropy. So the definition of entropy is negative sum probability times log 2 of pi. So this entropy of the source is this negative sum over all symbols. Pi times logarithm base 2 of pi. And in our case, this probability was ABCD. So for A was -3, logarithm base 2. Logarithm base 2 of pi is -3, because the probability of A is 1/8, and this 8 is 2 to the power of -3. For B is -1. For C is -2, because probability is 1/4, -2, and for D is again -3. So I insert this logarithm base 2 probability in this equation, and what I get exactly the same value. Why? Because this here is nothing else but negative word length of symbol A. This here is again negative word length of symbol B, blah, blah, blah. And this minus and minus are cancelled, and I get exactly the same expression as shown here. I multiply the the word length in bits for each of the symbols with the probability of this symbol. So again, this sum is then nothing else but, okay, not the sum, but 1/8, this is probability of symbol A multiplied by 3, because minus and minus is +3. Then probability of symbol B multiplied by 1, because this probability is 2 to the power of -1, 1/2. For C is what? 1/4 times 2 and plus 1/8 times 3. And again, I get 1.75 bits per second. Well, not per second, per symbol. So the entropy of such source is equal to 1.75. And this 1.75 is obviously less than 2 bits. 2 bits, because if I would use a simple binary code for 4 symbols, so binary code, ABCD, for example, 0, 0, 0, 1, 1, 0, 1, 1. If I use fixed word length for each of the symbols, then of course the average word length of average number of bits per symbol is 2. In binary, so this average word length is 2 bits. I simply take the first logarithm of number of symbols, n symbols. So I take the first integer value that is larger than logarithm base 2 of number of symbols. In our case, this number of symbols is 4, and we get 2. if I would have 5 symbols, then I should use 3-bit binary code, because with 2 bits it is not sufficient. But with Huffman code, it has variable word length depending on the probability. If I add the 5th symbol, maybe it would be still below 2 bits per symbol in average, in comparison with 3 bits per symbol that I need in the case of binary code. Okay? So in this synthetic example, the entropy and the average word length were the same. So this entropy is 1.75, and the average word length is also 1.75 bits per symbol. But do you think that this fact is always true? Or maybe it is just an example, classroom example, synthetic example that fulfills this identity. So what would you say? If I use these Huffman codes, what would be the expected word length in comparison to the entropy of the source? Of course, it cannot be better. So the entropy is always lower bound. The average word length always has to be equal or greater than the entropy of the source, because the entropy is the measure of the information quantity in the source. With any of the codes, ideally you should have this, equal to entropy. But in the real case, you get worse than that. How much worse than that do you expect? And what is the critical combination for probabilities where there is a larger difference between the average word length and the entropy of the source? In this case, the difference is 0. So we are operating exactly on this lower bound. We cannot be better than that. In this synthetic example, what I have chosen here, that these probabilities are exactly the power of 2, negative power of 2, 2 to the minus 3, 2 to the minus 1, blah, blah, blah. And for that reason, since these probabilities are such that they are just negative integer powers of 2, I can construct this ideal coding table, and the average bit rate is equal to the entropy. But of course, the actual probabilities, they don't have to be such nice negative integer powers of 2. They can be any real number that add up to 1 for all of the symbols. And for that case, the average word length would be close to entropy, but worse. So always greater than the entropy of the source. And what we have to answer is how much worse. How much worse do we expect that this average bit rate is in comparison to the entropy? And what is the critical combination of probabilities that would create the average word length that is significantly higher than the entropy? So do we have any idea of such a combinations of probabilities? Just, for example, for a process that has only 2 symbols, A and B. So suppose that this probability of A is whatever, 0.9, and probability of B is 0.1. Okay, I have 1 and 2 symbols. This one is much more probable than the other one. PA is 0.9 and PB is 0.1. Of course, they sum to 1. And if I construct a Huffman coding tree, then since I have only 2 symbols, I have 2 leaves. I start from the root, probability 1, and I end up either with A or B. So this is 0.9, this is 0.1, and these 2 are sum up to 1. And what is the average bit rate? probability of A multiplied by word length of A plus probability of B multiplied by word length of B. So this is 1 times 0.9, and this is 0.1, so 1 times 0.1. I get 1. Okay, so the average word length is 1, either 0 or 1. I use combination, for example, 0 for A and 1 for B. Okay, and the average word length is 1 bit per symbol because I have two symbols. So I transmit either 0 or 1 symbol. And what is the entropy in this case? So the entropy of such source is, so negative sum 1 to 2 pi log 2 pi, and that would be, sorry, that is 0.9, that is probability of A, times logarithm base 2 of 0.9 with minus sign. Because this is negative, so this negative value is cancelled with this minus. And again, minus 0.1 times logarithm base 2 of 0.1. And what do I get? I get value that is much lower than 1 bit per symbol. Just to check. So, I have to compute. Okay, if I start the MATLAB here, hopefully it will work. No, it will not work here, but I will start MATLAB here. Okay. So now if I write here, let me check if it has log 2. It has, okay. Log 2 of 0.9 times 0.9 and plus log 2 of 0.1 times 0.1 with negative sign. So it is 0.469 bits per symbol. So the entropy of such source is very low, almost twice lower than the average bit rate based on Huffman coding. So 0.469 something. Okay? So if I would increase the probability of symbol A and decrease the probability of symbol B even further, so not 0.9, 0.1, but 0.91, 99, 0.01. Okay, so I increase the probability of symbol A and decrease the probability of symbol B, what would I get? So I add 1.9 to the first probability. So logarithm base 2, 0.99 multiplied by 0.99 and logarithm base 2 of 0.01 multiplied by 0.01. And I get minus, okay, actually, of course it is minus, so 0.08 bits per symbol. So the information quantity is very low because you observe constantly A, and only in average in 1 over 100 times I observe B. Then again, A, B. So the information is always very small quantity of information observed in such sequence. So it is always A and only sometimes B. And that is the reason why this entropy is such a low value. So with this PA equal to 0.99 and PB equal to 0.01, they sum up to 1, I get entropy which is 0.0808 bits per symbol. 0.0808. Okay, and of course, in limit case, if I would still increase the probability of A by adding another 9 and by adding another 0 into probability of B, I will reduce this entropy even further. At the end, in the limit, it will be 0 entropy, practically 0 entropy, because you constantly observe A, and only 1 in a million you observe A. And the entropy is almost 0 bits per sample. What you need with Huffman coding is always at least 1 bit. I cannot have less than 1 bit per sample. And for that reason, the Huffman code is always suboptimal in comparison to the entropy by at most 1 bit per symbol. So at most 1 bit per symbol is the suboptimality of the Huffman code regarding the average bit rate required to encode the symbol sequence in comparison to the entropy. So I operate at most 1 bit suboptimal in comparison to the entropy. So with Huffman code, so the average word length is always less or equal than the entropy of the source plus 1. So in ideal case, the word length is exactly equal to the entropy. So it is definitely less than entropy plus 1. But in the worst case, this average word length of Huffman code is by 1 bit suboptimal for per symbol than the entropy. Okay? So this is the suboptimality. 1 bit per symbol. 1 bit per symbol suboptimality. Okay? And definitely it depends on the statistics of the source that you are encoding. If the statistics, if in such school example, like this one, I have prepared the example where the entropy and the word length are exactly equal. But if you have one of the symbols that has much greater probability in the end than all other symbols, as it is shown here or here, then for that case, the Huffman code cannot achieve entropy rate. So it is always suboptimal. How much suboptimal? At most 1 bit per symbol suboptimal. Okay? I hope this is clear. Do you have questions regarding this? So we will have such examples in the midterm exam. Then, okay, this is the statistics of the source. These are the probabilities. Construct Huffman coding tree. Or decode this sequence based on the given coding tree. So the examples of coding and decoding. If I go back to the presentation, okay. This would be sequence that I'm trying to encode. And this sequence has exactly the probability according to the table. So this is the probability of each of the symbols. I have 8 symbols at the output, and B is observed 4 times. So the probability of B is 1/2. Then in these 8 symbols, I observe C 2 times, C and C. I observe A only once, so the probability is 1/8. And I observe what else? D, only once. Okay? And now I create a encoded sequence. So this is encoded binary sequence with variable bit length, word length for each of the symbols. So B is encoded with 1. Then A, according to the table, is encoded with 0, 0, 0. Sorry, 0, 0, 0. Then D is 0, 0, 1. So 0, 0, 1. Then I have 2 times B, 1, 1. Then I have C. C is 0, 1, 0, 1. And finally, I have again B, that is 1, and again C, 0, 1. So if I count now, how many bits do I have for the whole sequence? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I have 14 bits. I have 14 bits for 8 symbols. And that is exactly 1.75 bits per symbol. So in this case, I have created an artificial sequence of symbols that has exactly the probability of observation given in the table. Okay? And I have encoded this sequence with Huffman code. I ended up with 14 bits for the whole sequence, and these 14 bits for 8 symbols give exactly the average word length of 1.75 bits per symbol. With binary code, this would be 16 bits, so 2 bits more than with this optimal Huffman code. Okay? Blah, blah, blah. And it says here, in the case that the probability of each of the symbols is not negative integer power of 2, as was in this synthetic example, or if the quantity of information per symbol is not integer, because we see that this information quantity per symbol was, as I have written here in the table, 3 bits for symbol A, 1 bit for symbol B, blah, blah, blah. If this is a real number, not an integer number. In this case, of course, we have to use the first larger integer value for this probability, this logarithm 2 probability, and that is the reason for suboptimality, that the average word length is up to at most 1 bit longer than the entropy. It says here. And this extreme example was shown. So if I have 2 symbols, where one symbol is much higher probability than the other, then the entropy is very low, while at the same time the Huffman code must have at least 1 bit per symbol because it has this branching A or B, and the average word length is 1. So the other approach, how to solve this problem of suboptimality, was addressed using the so-called arithmetic coding, and this it was introduced by this guy. He was working for IBM. He is from Finland originally, this Jorma Risanen. While working at IBM, he devised this special algorithm how to have the code that is more efficient than the Huffman code, even when the probabilities are such strange, where one symbol has much higher probability than all of the other symbols. In a way, how? In a way to encode the whole sequence of symbols with a real number. And this real number is some high resolution number between 0 and 1. Okay, so we have a real positive number from 0 to 1, and this real number with many digits encodes the whole message. So not only single symbol is encoded with a variable bit length word, but the whole sequence is encoded as a real number. And based on the value of this number, I will be able to reconstruct all of the symbols that are hidden behind this number, the whole sequence. And this algorithm is called arithmetic coding. And the reason why it is not used that oftenly is the fact that it was protected with a patent. So the IBM had a patent on this algorithm, on this principle. And if you would like to use this arithmetic coding, you had to pay IBM for the royalties for using this patent. And that is the practical reason why people more often use Huffman codes, which are suboptimal in comparison to the arithmetic code. Okay, and now we'll try to explain, or before the break, just to introduce how this concept of arithmetic coding is constructed. So suppose that in our example, the source has 6 symbols, A, B, C, D, E, F. So we have 6 symbols, and one additional symbol, this $sign, will be used to represent the end of the sequence. So I have to use like special symbol that will symbolize, okay, this is the end of sequence. Okay? And I will have to assign code or whatever also to this special symbol as well. And the next row gives the probability of each of the symbols. A, B, C, blah, blah, blah. And this, again, add up to 1 because they are probabilities. And the last symbol, this $sign, it also has probability of 0.1. And that would mean that in average, the whole sequence is 9 symbols long. So probability of changing the sequence, the new sequence is 1 in 10. So I have 9 symbols in a sequence, then end. Again, 9 symbols in a sequence, then end. So in average, this 0.1 means that the average length of the sequence is around 9 symbols, okay? And now I assign an interval to each of these symbols of the dictionary. These intervals are their width. The width of the interval is exactly equal to the probability of the symbol. Okay? So the first interval from 0 to 0.2. Second interval from 0.2 to 0.3 because the probability of B is 0.1, 1 over 10. Then for symbol C, from 0.3 to 0.5 because this is probability 0.2. Any real number from this interval, 0.3 to 0.5, would be symbol C. So I can choose any real number that is larger or equal to 0.3 and less than 0.5, and this real number would be used to represent symbol C. Okay, so this is the partition that is used to represent each of the symbols as an interval between 0 and 1. Because, of course, at the end, the last interval must end up with 1, since the total probability, sum of all the probabilities, is equal to 1. Okay, so if the symbol is very oftenly observed, its corresponding interval width would be large. In this example, the largest width are of symbol A and symbol C, so they are observed in 1/5 of the cases. Okay? And the least probable symbol in this example is this F and D. They have probability 1 over 20. Okay, now to explain this, how encoding is performed. Okay? This image is very important, and this table that shows the way that I'm encoding the sequence. So I'm trying to encode the whole sequence, CAEE $sign, with a single number. Okay? So I start with the first symbol, symbol C. Symbol C, it defines that this interval for symbol C must be between 0.3 and 0.5. Okay? And now I restrict my interval of interest only to this subset, only from 0.3 to 0.5. And depending on the subsequent symbols, I will use a real number in this range to encode all the false. But as soon as the number is between 0.3 and 0.3 and 0.5, I will know that the first symbol in the sequence is C. Okay? So what I do, so I say, okay, this first interval is from 0.3 to 0.5. Its width is equal to 0.2 because this is the probability of symbol C. Now I will subdivide this interval from 0.3 to 0.5 in the same way that I started for the first symbol. And that is shown in this picture. So for the first symbol C, I have started from the interval 0 to 1. And I have chosen this interval from 0.3 to 0.5 because I have observed the symbol C as a first symbol. Now this interval is subdivided into subintervals exactly in the same way as in the first symbol in the sequence. So from 0.3 to 0.5, I subdivide relatively the same way as I did here. So the next symbol is symbol A. CA. And this A means it must be subinterval 0.2 wide at the beginning of this interval of C. And that means that this 0.2 is multiplied by probability of A. Probability of A is again 0.2. And I get 0.04 as a width of this interval, 0.04. And I add this starting value of this interval 0.3. So I have here starting interval 0.3, and the ending of this subinterval is 0.34, because this 0.4 comes from 0.2 times probability of A, that is also 0.2, and product of these two probabilities is 0.04. Okay? Now I have that the real number, any real number in this interval, from 0.3 to 0.34 would represent the sequence CA. So any real number in this interval, it means the first letter was C and the second letter was A. Now I repeat this concept again, but now I subdivide this interval, 0.3 to 0.34, based on the subsequent letter, and that is E. So this 0.3 to 0.34, so the upper limit is 0.34, the lower limit is 0.3. I select the range for symbol E. Okay? And if I compute this range for symbol E, it is 0.322 for the lower bound up to 0.334 for upper bound of this subinterval. So 0.322 up to 0.334. Okay, 0.322 up to 0.334. Any real number in this interval would be used to represent the sequence CAE. Now the width of this interval is equal to 0.012 because it is actually a product of probabilities. C times A times E. So I have multiplied, so C, A, so it is 0.2 times 0.2 times 0.3. So that is the current interval width. So as I add additional symbols, I get narrower and narrower intervals. So it was probability of C, then A, then E. This was 0.2, this was 0.2, this was 0.3. what? 0.3. So if I take the product, I get this probability of observing the whole sequence CAE, and this probability is equal to how much? To 0.012. 2 times 2 times 3 is 12, and 3 decimal places, and that is 0.012. Okay? And I go further. Finally, I have this dollar sign, and I have to subdivide this last interval from 0.33184 to 0.3322. And the width of the whole sequence, of the whole, the probability of the whole sequence is then what? Is simply probability of C times probability of A, of E, of dollar. So the last interval, its width is equal to the probability of the sequence, because product of this probability. So this product is actually probability of sequence. Okay? And now all I have to do is to find the real number as short as possible that has, let's say, binary encoded value, as short as possible, to represent any value, any real value in this interval. Okay? And this real number with binary encoded value would be used to represent the whole sequence. Okay? And this binary value in our example would be which one? This is the binary value of 12-bit binary fraction. So I have deduced that the necessary length of the fractional representation is at least 12 bits. I will explain that after the break, why exactly 12 bits. And this 12-bit fractional number is which one? It is this one, 0.33203125. This one is within the interval that I have selected after observing the last symbol. So this 0.33184 up to 0.3322. This chosen value is somewhere in between this interval. Okay? And that is sufficient. So it can be any number in between, and this number, this 12-bit number, would represent the whole sequence. So C, E, A, E, dollar. Okay? We will make a break now, and after break I will explain why exactly 12-bit number and how to get this value, that encodes the whole message. This value, sorry, where it is? This is this binary representation of this real number. So this 12-bit fractional number represents the real value that is within that last interval. Okay? This here is 2 to the power of minus 1, 2 to the power of minus 2, blah, 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 up to 2 to the power of minus 12. So that is nothing else but a fractional representation of a positive real number between 0 and 1. And this number is how much? 0.3323125. Okay? In decimal representation. And we will show that if we start from this value, we will decode exactly the sequence that we have sent. C-A-E-E-F, dollar, sorry. So C-A-E-E dollar. Okay, we'll make a break now, and after the break, we will describe how this decoding works. Okay, and why exactly this number, and why exactly 12 bits long. Okay? So, short break. Okay, so let's go further. So first of all, let me demonstrate how this decoding works. So we have started from this 12-bit binary fractional number. So beside this real number is the corresponding fractional binary representation. Which one? This one. So this, the whole message is encoded with a real number. That has a fractional binary representation. And this fractional number is 0.010, 101, 101, then 01 and 4 zeros. 01 and 4 zeros. And the actual value is what? This is 0 times 2 to the power of minus 1, or 0 times 0.5. Then this here is 1 times 2 to the power of minus 2, and that is 1 times 0.25. So blah, 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 and add up this together, and I get the final value that is encoded with this 12-bit binary fractional number. And this real number is how much? It is 0.33 2031 25. Okay? So I start from this value and I try to decode the sequence. First of all, I observe that this value 0.33213125, it is within the interval of letter C. Why? Because this interval of letter C is from 0.3 to 0.5. It is somewhere in between. And I say, okay, the first letter must be C. And if it is C, then what I have to do, I have to subtract 0.3, the beginning of the interval, and divide by the width of this interval, 0.2. So that is what I'm doing. I'm starting with this real number, and I subtract 0.3, and I get 0.032, blah, 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 and divide by the interval of the symbol C, interval width, and that is 0.2. The same thing is multiply this subtracted value by 5. And I get a new value, and that is 0.1601, blah, blah, blah. So this value here is nothing else but 0.33, blah, 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 minus 0.3 divided by 0.2. And this is the new value to decode. And this new value is then recognized. This value is within the interval for symbol A. Why? Because the interval A is from 0 to 0.2. So everything that is below 0.2 must be symbol A. So I deduce, okay, the next symbol must be symbol A. I have to subtract the lower bound of this interval, that is 0. So I subtract 0 from this, it is the same number. And again, I divide by the width of the interval for the symbol A, and that is again 0.2 because it has the same probability as symbol C. And I get what? It is the same value multiplied by 5. So this 160 multiplied by 5 is 0.800, blah, blah. Now I recognize this is within the interval for symbol E, because the symbol E is from 0.55 to 0.85. So that is the interval for the symbol E. 0.55, 0.55 to 0.85. Okay? So I say, okay, the next symbol must be symbol E. It must be symbol E. I subtract this value from this 0.8000 minus this, and I divide this difference with 0.3. That is the width of the interval for symbol E. And I get a new value. Again, it is in the same interval, from 0.55 to 0.85. Again, it must be the same symbol E. Again, I subtract 0.55, and I divide this difference by 0.3, and I get a new value, 0.953125. Okay? And the final value is within the interval corresponding to symbol $. And that means that is the end of the message. I don't have to go further. Now I know this is the last symbol. I have decoded the whole sequence. Okay, the whole sequence is then CAEE $. So now we understand that it works. We have shown it works. I have started from any real number that is within the last interval. The last interval was from 0.33184 to 0.3322. So any real number in this interval would give the same sequence. We have chosen one real number that has short binary fractional representation. And that short number, or binary 12-bit fractional number, is which one? This one. 0.33, 20, 31, 20, 31, 25. Obviously, this value is really within this final interval. But I could have started from any real number within this interval. For example, I don't know, 0.33. It would decode into the same sequence. So this is only one possibility to encode this value, this real number within this interval. Why exactly this one? Because this one has the shortest binary representation. If I would try to represent number 0.33 with binary bit code, I would need a larger number of bit positions. Okay, so this is the number that has the least number of binary bit position, and that is within this interval. So this is the criterion. So I have to choose binary fractional number. It is nothing else but a fractional expansion of a real number on a fixed number of bit positions. And I want to find such binary fractional number that has the least possible number of binary positions, and that is within the interval, the last interval that is used to encode the whole sequence. Okay, and now, how have I found this 12? That is the next question. Why exactly 12? 12 bits. Why exactly 12-bit binary fractional representation? This 12 comes from the last interval width. So this last interval width was, the width was how much? The width was, so this difference, the width was how much? 0.00036, 0.00036. Okay? And this is nothing else but the probability of the whole sequence. So this value, this W, is nothing else but probability of C multiplied by probability of A multiplied probability of E, probability of E, and probability of $sign. And that is equal to 3 zeros, 36. Okay? So that is what probability of the message. Of the whole message. And now, what I have to do, I simply have to take the logarithm base 2 of this W and find out that this is minus 11 point, how much? Minus 11.44 bits. Then I have to select the first larger integer, larger than this real value, and this first larger integer is 12. So I have to use 12 bits in order to encode this value within the interval that is this wide. The interval bit is 0.00036. Okay? I have to use 12-bit binary representation, binary fractional number, and I claim that there always exists at least one number within any interval of this width. Okay? That is the claim. The claim is, it says here, blah, blah, blah. In any interval of the width Pm, this W, it is nothing else but the probability of the message. So, product of probabilities of all of the symbols within the message. So, any interval that is Pm wide, within 0 to 1. So, there is a real number that can be represented using binary fraction, whose number of binary positions is at least integer number, first integer number greater than log 2 of 1 over Pm. Okay, so it is nothing else but minus log 2 of Pm, so it is Pm logarithm 2 of 1 over Pm, and that is the required number of bits, the minimum required number of bits to represent such a real number. And I claim that there always is one binary number within any interval of width Pm on any starting value. So this interval that is Pm wide can start from any real number between 0 and 1. Of course, not exactly 1, but so from 0 to Pm, from whatever, 0.1 to 0.1 plus Pm, or any real number up to 1 minus Pm up to 1. Okay? So I can take any interval that is Pm wide within 0 and 1, and I will always find one real number that has binary representation with b bits, and this b is ceiling, or first larger integer of log 2 of 1 over Pm. So I take this ceiling value. I take first larger integer larger than this real number that is logarithm base 2 of 1 over probability of the message. And I get, in this example, I get the value of 12, because the original log 2 is 11.44, sorry, 11.44. For that reason, I select 12 bits, and there exists 12-bit binary fraction that is within the interval, which one? This one. 0.33184 up to 0.3322. Which one? This one. That is 12-bit binary number that is within this interval and which encodes the whole message. Okay? Now we have encoded the whole sequence with 12 bits. Okay, I have sent the number as a 12-bit fractional number, and these 12 bits, they represent the whole sequence. So all of this that I have sent, this CAEEF, CAEE$, the whole sequence is represented with this binary number that has this real value, okay? So what is the suboptimality of such encoding scheme? So what will you say? This value, this logarithm base 2 of 1 over pm, is actually the quantity of information in the whole message. And that means that we have encoded the whole message with the least possible number of bits and with at most 1 bit suboptimality. Because in our example, this logarithm base 2 of 1 over pm might have been, for example, 11 point log 2 of 1 over pm. It might have been 11.0001 bit. Okay? And again, we had to use this ceiling, first greater integer from this real number, and this ceiling operator would have selected that I have to use 12-bit code for the whole message. So I see that this suboptimality is at most 1 bit suboptimal, but for whole message. Sequence. So the suboptimality of the arithmetic code is 1 bit, but not per symbol, as it was the case for Huffman code, but the suboptimality is 1 bit for the whole message. And that is the reason why the arithmetic code is much more efficient than the Huffman code. Okay? This here describes the decoding process. Okay, we start with this number. We try to find which interval this number is within. Then I select this symbol corresponding to this interval. I subtract the lower bound of this interval, and I divide by the probability of that interval, and I get the new number. And this modified number is then again used as an input for the next step, for the next symbol. And that was illustrated here. So this value 0.3320 blah blah is within the interval for C. I subtract 0.3, that is the lower bound for the interval C, and I divide by 0.2 and I get the new number. And I repeat the procedure until I get the final symbol. And the final symbol is this dollar symbol. It tells me I have to stop. I have come to the end of the sequence. I have to stop. That is the last symbol, and I do not repeat it anymore. Okay, so now suppose that we have made an error. So suppose that the last bit in this 12-bit representation was wrong. It was not 000, it was 001. And the real value that is behind this binary representation is not this ideal value. This ideal value was 33203125. It is modified 332275390625. Okay. Is it within this interval? It is not. We see that this value exceeds the upper limit of the final interval. So this must be at most 000, not this value 7539 blah blah blah. So definitely by adding this binary 1 at the end of the message instead of binary 0, I have one value that is without this last interval that encodes the whole message. And now I can try to find out, if I start from this value, from this real number, what would I get? The same procedure. So I repeat the decoding procedure, but starting from this modified value of the real number, not the proper value, but this modified value, and I decode the sequence of symbols. I get, at first, the same set of symbols, C, A, E. The first three symbols are correct. But the fourth symbol, that was supposed to be E again, is wrong. It is decoded as F. Now I have to repeat until I get the last symbol equal to $. And if I repeat this procedure, I get C, A, E, F, A, B, E, A, $. And if I check, this message is actually represented using this 26-bit long fraction. So this wrong message was represented with the same first part. It has this wrong last bit 1. But after that, it has additional 12, not 12, but 14 bits of 0. So this value here, this 332275, actually represents one 26-bit long fraction that encodes a different message that is not 5 symbols long plus $, but we can see 1, 2, 3, 4, 5, 6, 7, 8, 9 symbols long plus $. So only 1 bit error could significantly affect decoding of the sequence. We get completely different decoded sequence based on a single bit error. So only 1 bit was toggled, and the decoded sequence was completely wrong. Such problem exists with Huffman codes as well. So if I had Huffman code, this prefix code, and suppose that any of those bits was toggled. For example, this one that was B, this double B, BB was 1, 1. And suppose this was toggled from 1 to 0. So I would decode this last symbol, it was 0, 0, 1, that was this D, and after that I get 0 here, 0 here. And 0, 1 is what? 0, 1 is C. Okay, so instead of having BB, I get here 0, 1, it is C. And then again C. Instead of BB, I get C, and then after that C. So the message is completely changed. If I make a single bit error, the number of symbols might be different. The number of decoded symbols might be affected by single bit error in the bit stream. And that is the reason why such entropy codes are prone to bit errors. And if you have a system where this bit error is not 0, if you had some random bit error, like on radio communication channels, then you have to send some kind of redundancy check in the whole block, just to check whether the whole block was correctly received. And only then you can use these entropy codes to decode the message and be sure, okay, the message is correct. Entropy codes have reduced the average rate, but nevertheless, with some kind of cyclic redundancy check, I have ensured that this message is correctly decoded. But without this redundancy checking or coding, I cannot be sure that this decoded message is meaningful, because a single bit error in the transmission channel can cause complete loss of information on the decoding side. Okay? That was, I guess, more or less it we have covered now. It shows at the end one example. This is a decoding table for the last case where we have this wrong last bit is shown here. So we start from this wrong real number that is without this interval, and at the beginning the symbols are the same, C, A, E, but the fourth symbol was wrongly decoded because it fell into the interval of symbol F instead of E. And after that, that was A, E, B, E, A, and finally we got $sign that shows we have the last symbol. And the sequence was completely wrong, except for the first 3 symbols, completely wrong. The example shown here, it shows the image. So this here is grayscale image. But only certain values of gray level are present in the image. And this here shows the histogram of gray levels. So how many pixel positions do I have? I have altogether 20 by 20 pixels, 400 pixels. And if I count how many times I observe certain value of gray level, I have discrete probabilities for only certain levels. So for example, for level, I don't know how much this is, 10. For level 10, something that is quite dark, I have 16 pixels that have this value of 10. Almost black. Then I have another 16 pixels that have value 20 or whatever. So I have only discrete a number of different levels present in the image. So not all the levels from 0 to 255 are present. Only certain discrete values are present in the image. And now I have how many symbols? Exactly how many different levels I have. So some symbols that do not appear because this value, for example, this value 50, it has probability 0. 51, probability 0. But finally I get this 70 something, probability something. And now I compute that based on the entropy, okay, based on the entropy, if I would use the entropy to encode this image, all the values are from 0 to 255, like 8-bit value, due to the fact that some values have 0 probability, the actual entropy per pixel is 4.26. So practically 1/2 of the normal word bits. Normally we would have 8 bits per pixel to encode the value from 0 to 255. But since only discrete values of level are present in the image, the actual entropy is much lower than 8 bits per pixel. So with 8-bit encoding, I would need 3,200 bits for the whole image. But if I would use the entropy code, it is practically almost 1/2 of the bits, 1,707. But this here, it only shows the entropy, not the actual code. Okay, in the actual implementation, I would have to use either Huffman code or the arithmetic code, and then the average length would be slightly above the entropy, okay? At most, 1 bit for the whole message above the entropy, or 1 bit above the entropy for each symbol, okay, per symbol for the Huffman code. So it shows here that if these values are discrete, if only certain gray levels are probable or possible and others are not, because they have 0 probability, then the information quantity in such image is definitely lower than 8 bits per pixel. It is 4.2 bits per pixel. Okay? We have so far learned that Huffman encoder and arithmetic encoder both are entropy encoders, and they are lossless. So we start from the sequence, we generate code, encoded sequence, and after decoding, I get the original message without any loss. So they are lossless coders. And both of those coders, they achieve the compression based on the entropy of the source. That this entropy is finite. The source has finite entropy. It has statistics for each symbols observed from the dictionary. So we have considered only memoryless sources, where each individual symbol is generated irrespectively of previous or subsequent symbols. So the probability of each symbol in the sequence is independent of preceding or succeeding symbols. And for such encoder, the bound is given by the entropy, and the average word length per symbol can approach this theoretical minimum defined by the entropy. Can approach. In ideal case, on this school example, we have equal word length and entropy, because the probability of these symbols were integer powers of 2. And for that reason, I could construct the code that has exactly integer word width as optimum value. The additional advantage of the arithmetic code is that it can support this fractional code's length. With Huffman code, the code length must be integer. 1 bit, 2 bit, blah, blah, blah. I cannot have 1.3 bits. So per symbol, per individual symbol. So for each of these symbols, it can be 2 bits, 2 bits, 2 bits for the binary codes. For the Huffman code, it was again 3 bits, 1 bit, 2 bit, 3 bit for each individual symbol. It cannot be 2.5 bits for symbol C. It must be integer number of bits per symbol. And that was the reason why this Huffman code is suboptimal in comparison to the arithmetic code. Arithmetic code enables that this word length of given symbol is a real number. Okay? And how much? It is simply the logarithm base 2 of 0.2. So that is the effective word length or word width of symbol C. It is simply log probability of 1 over 0.2. Log probability base 2 of 5. So that is the effective symbol word length for symbol C. For symbol E is again logarithm base 2 of 1 over 0.2. Blah, blah, blah. So the arithmetic codes enables fractional representation for word width. On the other hand, with the Huffman code, we must have integer word width for each of the symbols. That is the reason why the arithmetic code is superior to the Huffman code. Okay? Blah, 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 we have described. So we have introduced the definition of coding and compression, types of coding and different lossless, lossy, blah, blah, blah. We have defined the information, the measure of information, that is the entropy. We have introduced entropy coders and example of codes with variable word length based on the probability of each of the symbols. And these were Huffman codes and arithmetic codes. Okay. And now, on the next lecture, we start to relate the entropy and the quality. Okay, so far we have discussed quality of quantization. So if I quantize the signal, I want to measure what is the error introduced by quantization. We have shown this signal to quantization noise ratio, defined this measure. Now we have introduced the entropy. And finally, we want to relate how this entropy is related to the quality. Okay, and that will be the subject of this presentation. Okay, so we start from continuous dictionary. That is the first fact. So ideally, the process we start from is not a discrete probability process like the one shown here. We have symbols A, B, C, D. They have discrete probabilities, probability of A, B, C, and D. What we have a real number. So we have a certain value that was measured by AD converter. And we want to encode this real number value in order to achieve compression. And the fact is that by quantization or by AD conversion, what we are doing, we are converting this amplitude continuous process into quantized, into integer process that has discrete probabilities of each of the observed values. Because at the end, at the output of the AD converter, for example, if I have AD converter that has three bits with two's complement representation, okay, the same example as before. So I have .75, 0.5, 0.25, 0, minus 0.25, minus 1/2, minus 0.75, and minus 1, 0. So this is fractional representation with Q1.2 binary number whose complement. Okay? And I have started from a real value. I have started from X element real numbers, set of real numbers. But after this quantization, I have ended up with symbol E, integer symbol, that is element of this range. Minus 4, minus 3, minus 2, minus 1, 0, 1, 2, and 3. So these are all possible values at the output of this quantizer. And now what I have actually probability, so observing value index minus 4. Because this value, index minus 4, it represents certain range of values, of real values. So this range is from minus 1 to the midpoint between 0.75 and minus 1.0. And this midpoint is 0.8125, I guess, if I'm not wrong. Okay, this is the midpoint between these two values. Is it correct or not? This will be 0.125. 0.125, then it will be 0.875. Sorry. Okay. Okay, so this value minus 0.875 is the midpoint between minus 0.75 and minus 1. So all values that are within this range are encoded with a symbol minus 4, and this symbol minus 4 has certain probability. It is a probability that this real number would be in this range. If I want to have this next symbol, symbol 3, it is in between this midpoint and this midpoint. Okay? So any input value that is in between minus 0.625 up to minus 0.875 is encoded, this range is encoded with symbol minus 3, and this symbol minus 3 also has certain probability. So although the input alphabet, this X, it was a real number, after quantization we have symbols. And these symbols are from the finite dictionary of symbols. And they depend on the chosen resolution of this AD quantization, or this quantization step, that converts this real value to this integer index representation. Okay. So it says here that in order to apply this entropy coder at the output of the quantizer, we have to apply the entropy code on these symbols. So what we get after passing this real value, so I have this real value, X element n, I have this AD converter, and the output, if I have Q1.2 representation, so I have actually 8 symbols, 8 possible symbols. Okay? And for each of these 8 possible symbols, from 3 to 1, 0, minus 1, minus 2, minus 3, minus 4, I have probability. Probability of symbol 3, blah, 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 to probability of symbol minus 1. And now I can construct the entropy coder. Construct entropy code. When do I have any gain based on this entropy code? What is the necessary condition to have binary, or to have the word length that is lower than 3 bits. So I have 3 bits here. So this word is 3 bits wide at the output of the AD converter. I have 8 symbols. So what is the necessary condition to have the average word length or number of bits per symbol that is lower than 3 bits?
One symbol has to be mostly common.
So definitely the probabilities must not be the same. So the probability of individual symbols should not be equal, because if the probabilities are equal, so if this pi is equal to p of blah, 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 and that is nothing else but 1 over 8, so 8 symbols, probability is 1/8. If it is so, we have no gain. Okay, we cannot have any reduction in the rate based on entropy code, because the binary code in this case is the optimal code. So if the probability of all of the symbols is equal, then the optimal code is the binary code. And if I would construct the Huffman table for such a case, so I have these 8 symbols from +3 up to -4. Each of these symbols has probability 1 over 8. So if I combine first 2 and last 2, then I combine these 2 and these 2. And I combine these 2 and these 2, and I'm at the root. Okay, and by assigning whatever, 0 here, 1 here, 0 here, 1 here, 0 here, 1 here, I have a binary code. So if the probabilities are the same, Huffman codes would give a binary code, because all of these probabilities are equal, and I simply combine 2 leaves that have the least probability, 1 over 8, 1 over 8, 1 over 8. Now it is 1 over 4, blah, blah, blah. But if the probabilities are not equal, then there is potential for bit rate reduction. For example, we can say typically this AD converter would have zero value more probable than some large value. So typically we would observe some value at the output of AD converter close to 0. Why? Typically, if you have speech signal, it looks something like this. Okay? And the whole range is adjusted to the dynamics of AD converter. So this is 0, 1, 2, +3, -1, -2, -4. And how many times we have observed this symbol 3? Only 3 times. So seldomly the signal would have large values. Only a few times for all of the symbols observed. Most of the time, this value of the signal is close to 0. So maybe 0, 1, -1. These are mostly observed values at the output of AD converter. And for that reason, if I use short code for these 3 values and long code so for larger values, absolute values, positive, negative, then I would have more efficient code. It would have a lower average bit rate than the binary code. So I would get less than 3 bits per symbol if I would construct some kind of entropy code based on such statistics. So for example, large absolute values are less probable than small absolute values. I would have Huffman code that has short codes, 1 or 2 bits in length for 0 or for 1 or plus, -1, while longer codes for 2, for 3, -2, -3. And that is the basis for rate reduction. Now it's 2 minutes after 6. We'll make now a break, and then we'll discuss how we can finally relate this average entropy rate at the output of the entropy coder. So I have what here? I have some average word length or average rate at the output of entropy coder. And I have quality. Quality is defined by the quantization step here. So the lower quantization step I use, I have higher quality. So I want to relate these two. What is the quality or the error introduced by quantization of the ideal real value in comparison to the rate, to least achievable rate after entropy coding. I want to relate these two. And we will show how these two finally end up to very similar expression that we have with the SQNR ratio, signal to quantization noise ratio. But instead of having these B bits per symbol, this binary code, B bits per symbol, B bits, we will have this entropy as a measure of rate and not a fixed rate of B bits per symbol. Okay? And just to show this final expression that we are aiming for, it is shown there. Okay, here. Okay, so we have remembered a similar expression for the SQNR ratio. We had this 20 times logarithm base 10 of 2, it was 6.02 bits. Multiplied by B, it was resolution of the AD converter, and plus some offset. We have the same thing here now, but instead of fixed B, it was 16-bit, 8-bit, 3-bit, blah, blah, blah. We have here the entropy of the source. Entropy of what? Entropy of these indices. So we have indices I, this value, 3, 2, 1, blah, blah, blah. They have entropy. And this entropy here is multiplied by this 6.02. So we have still this linear relationship between the quality and entropy with the slope of 6.02 bits per bit and plus some offset. And this offset, in the case of SQNR, it was related to this crest factor, to the ratio of the maximum value in comparison to the effective value. Here, this SQNR 0 is determined by something that we will call differential entropy. This h of capital X is a so-called differential entropy. It is defined by the statistical properties of the source that we are encoding. These statistical properties are like complexity of the source. If it is more easy source, easier for compression, or complicated source, more difficult for compression. So this differential entropy is a measure how much certain source is complex for reduction, for compression, for entropy reduction. Okay, that is just preparation for the final expression we'll try to derive, but after the break we'll show how we can get to this simple linear relationship between the rate and distortion. Okay? So, short break now, it is 6 minutes after 6. In 10 minutes, so we start. Questions? Okay. Okay, we can start further. So just to have the whole image in your head. So we start from a real number, x element r. Then we quantize with this AD converter this real number into some integer representation. We have this x quantized, and that was what? It was q times round of x divided by q. So the q was the step size. Q was the step size. And this value here is this index I. I have divided this real number with the step size, and after this I round this value to the nearest integer. And I get this I that was in this example element from -4 to +3 if the step size was chosen as 0.25. 0.25. And the input value was not whole real numbers, but ±1. So this x was the element from -1, x was the element of -1 up to +1 excluded. Okay? So what we have the quantized signal value, but we also have this input, this output, sorry. We have this index I that corresponds to this quantized value, I, at the output of AD converter. And what we have now we have this I that is entropy coded. So we have probability Pi for all I in the interval -4 to +3. And based on this probability, I can construct entropy code. For example, Huffman code or arithmetic code. Okay? And here, what I have number of symbols. For example, in this case, is 8 symbols if I use representation Q1.2. So 2's complement with 2 bits fraction. So this here is 3 bits wide. But I expect that the rate here would be close to the entropy of source I. So this age of I is the entropy of this source. To be correct, I should denote this source with capital I, and then this would be entropy of this source, capital I, where these symbols are from the dictionary -4, -3, blah, blah, up to 3. And hopefully this age of I would be less than number of bits, b equal to 3. Why? Because these probabilities are not equal. If these probabilities are equal to 1/8, I have 8 symbols, I have no gain in using the entropy code, because the optimal entropy code is the same as binary code. I have no rate reduction. But if the probabilities are not equal, if certain symbols have larger probability than the other, I can reduce the rate based on entropy code. And finally, I want to relate this, that is the output rate, with what? With error. And this error is difference between x, q, and x. So I take this difference, I take squared value, and I take the expectation. So the expected squared error between the original signal and quantized signal is the distortion. So this is distortion. Distortion is the expected square error between the original signal and quantized signal. What I expect that this distortion is directly related to what? To entropy. Okay? And why is this so? Because, of course, if I use, instead of 3 bits, if I use here 4 bits, then the step size is twice lower. Okay, and we know that this variance of the quantization error, so that was denoted with sigma e squared, was 1/12 of delta squared. So the expected squared error of a representation with AD converter that has a linear step size of delta is nothing else but step size squared divided by 12. And if I use 2 times smaller step size, because I have 16-bit AD converter, not 16-bit, 16 level, so 4-bit AD converter instead of 3-bit AD converter, then I have 4 times lower variance. I have 4 times lower variance of the quantization error. But at the same time, now I have not only 8 possible symbols here, but 16 possible symbols here. And definitely the entropy of such source is larger. And what I want to find is what is the relationship between the entropy and quality. So quality is defined by the distortion due to quantization, the difference between the quantized signal and its original value. And we know that this expected difference of the squared error is step size squared divided by 12. And the entropy, okay? Okay, that is just the basic idea of what we are trying to express here. Okay, so there are 2 possibilities how to encode this real signal. One possibility would be the following. I might limit what? I might limit the entropy. For example, I have to transmit this through some channel, and this channel has given capacity. I cannot transmit more than 3 bits per symbol in average. So I know this h of I is limited. Then I am trying to find what is the least possible step size delta that I will still have this entropy 3 bits per symbol. So I want to find out, okay, the entropy is limited. What is the smallest step size? What is the highest resolution I can use here in this quantization in a way that this entropy is still below the capacity of the channel. And that is called entropy constrained quantization. So I constrain the entropy, and I'm trying to find what is the highest quality that I can achieve with this entropy limit. So I want to design a quantizer that after the entropy code, so after entropy coding, this message must be contained within the capacity limit of the channel, and that is, for example, 5 bits per symbol, 3 bits per symbol, whatever. The other possibility is distortion limited quantization. And that means I want to achieve certain distortion. So for example, 30 bits, 30 decibels signal to quantization noise, and I adapt the entropy to achieve this quality. Okay, so that is the other possibility. I have a variable capacity of the channel. Whatever it needs to transmit the information, I have this capacity. But of course, I want to use the least possible capacity to convey the information. And for that case, I would limit the distortion and say, okay, it must be 30 dB signal to noise ratio, so I define this minimum step size to achieve this distortion, and then find out what is the required entropy for such source. Okay, then the channel capacity must be at least that much to transmit with this quality the signal through the channel. Okay, so that is the coding with limited distortion, or with the distortion bound. So the reconstructed signal must have the error of quantization, which is at most defined by this bound. It must be better or at least equal to this bound for distortion limit. So the issue is then how to design a quantizer that minimizes this required channel capacity at the same time achieving this distortion bound. The answers to this question is given by the information theory and one particular branch of this information theory that relates quality and rate is source coding theory, and especially part of this source coding theory that is called rate distortion theory. And this rate distortion theory, exactly the one that we are trying to introduce here, was proposed by some fundamental papers by Claude Shannon in 1948, at the time he was working in so-called Bell laboratories. It was like a telecom provider, the biggest telecom provider in US at the end of Second World War, and he was working in this AT&T Bell laboratories, and at that time he introduced this rate distortion theory. Okay, and practically all of the modern coders that are used in media systems, multimedia systems, they intensively use the knowledge of information theory. So this is not just a theory, it is very much applied in the practical solutions. We will illustrate the application of information theory on an example of scalar quantization with limited entropy. So entropy constrained scalar quantization, that is the abbreviation ECSQ, entropy constrained scalar quantization. What we are trying to find, we want to constrain the entropy of this output signal. So these indices are entropy coded, and we want to constrain the entropy of these indices by suitable design of AD quantizer, by suitably choosing this step size. Okay, this entropy constrained scalar quantizer, it is practically the simplest possible example that you would apply this information theory to, and to demonstrate how this information theory is used to find the final result. But nevertheless, although it is like a school book example, it is nevertheless used in practical solutions. So many codecs that you would encounter today, they use this entropy constrained scalar quantization concept, especially when it comes to coding of audio signals. These audio signals are typically encoded with this kind of entropy constrained scalar quantization. They have very high efficiency, especially if these sequences are very long and if they are statistically independent. So if the particular entries in this sequence are statistically independent, then practically this very simple entropy constrained scalar quantizer is the optimal solution for encoding such sequences. Okay, it says here different application where this entropy constrained scalar quantization can be used in practice. So either by quantizing the signal samples in the original time or in spatial domain. So in time domain if it is a time signal, speech or audio, or spatial domain if it is image or video. On the coefficients, on the transformation coefficients of the signal in some of the transformation domains. And we will use this here for your laboratory exercise. So your first laboratory exercise would be, you would transform a block of samples of the input signal to discrete cosine transform domain. So using discrete cosine transform, that is a very simple block transform. From 8 samples, I get 8 coefficients. And then you would apply entropy constrained scalar quantizer to this 8 transform coefficient. Not directly to the signal samples, but to the transform coefficient of this DCT transform. It can be also used to so-called sub-band signals with structure that use these filter banks to divide signal into different or several spectral bands. So we have this spectral separation of signal into different bands, and I quantize each of these sub-bands with individual quantizers that also use this entropy constraint scalar quantization. Blah, blah, blah. Without going further, okay, the input to this process is this digitized media signal of nominal accuracy, nominal resolution. And this signal is additionally quantized here in the concept of this AD converter. So this here, this x of r from -1 to +1, that is this nominal raw signal. It comes from the very high resolution AD converter that is really at the input of the media chain. And now we are additionally quantizing this almost ideal, let's say, signal to see what would be the relationship between the quality if I introduce additional error due to this coarse representation with large step size in comparison to the rate of these indices, rate of these entropy indices. Okay? Typically, we use this bipolar fractional representation for this input signal. So this -1 to +1 is like a normalized input range for this real number. Okay? And now this example here shows what happens if I have only 5 quantization levels. From -1 to +1, I divide this input range of a real signal into 5 equidistant ranges. Each of these ranges is 0.4 wide. 5 times 0.4, we have this 2 as dynamics from -1 to +1. Okay? And then each range is represented with a central value. For example, this central value of +0.8, it represents the signal range from 0.6 to 1. So if the input signal is from 0.6 to 1, it is represented with the value of 0.8. If it is within 0.2 to 0.6, it is represented with the value of 0.4. So this kind of quantization shown on the slide is nothing else but simply dividing the input value x by 0.4. What is the step size? So this is delta. This is the step size, delta. I take the first closest integer, round, and then again I simply multiply this index I. I multiply this index I by the step size, and I get the quantized value x hat. And this x hat is this 0.8, 0.4, blah, blah. So possible quantized value are those. So these are 5 possible quantized values for indices 2, 1, 0, -1, -2. So these are these indices I, and these are the corresponding quantized value for indices from -2 to +2. Okay? Now I want to find what? I want to find the it is shown here. So this quantization value -0.8, -0.4, sorry, 0, 0.4, 0.8, blah, 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 while the ideal value was shown with this dashed blue line. Okay? And of course, this error is like a sawtooth wave. I have negative error, or in this case, positive error, whatever. Subtract what you subtract from. So if it is half step size negative, half step size positive, half step size negative, blah, 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 like a sawtooth. That is the error between the ideal real value and the quantized value, this red value. Okay? Do I have this error shown? Okay, this green line. So this green line is the error between the ideal real value and the red quantized value of the signal. Okay? Now what I have to do also, I have to find what are the probabilities of each of the symbols. So what is the probability of symbol -2, -1, 0? Okay? Why? Because in order to compute the entropy, h of I, so to find this value, I must find the probability of each of the indices. -2, -1, blah, blah, blah. Okay? So first of all, I have to somehow, based on the process, find what is the probability for each of these symbols. -2, -1, 0, and so on. Because I will use this probability to construct entropy codes, and in ideal case, the average rate at the output of this entropy code would be equal to this lower bound to the entropy. Okay? And it says here, so the output process, this here, these indices at the output, these indices I, so they are from this set of -2, -1, 0, +1, and +2. What I have to find out, what is the probability of -2, what is the probability of -1, blah, 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 up to probability of +2. And this probability, if I know them, I can compute easily the entropy of this output of AD converter. So this AD converter, it has only 5 levels, and it has this indices I. I want to find the entropy of this, of the source. What is the entropy of these indices? And by definition, since it is a discrete process, this entropy, this h of I, is negative sum pi log 2 pi. So I have to simply take, okay, what is the probability of -2 multiplied by log 2 of 1 over p minus 2. Then plus probability of -1 logarithm base 2 of 1 over p minus 1, and blah, 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 up to p2. So p2 times logarithm base 2, 1 over probability of symbol +2. Okay, and I add up together these values, and I get the entropy of the output indices. Okay, as shown here. Okay, now the question is, can I find this from the probability density function of the process itself? These probabilities, can these probabilities be found from the probability density function of the process X that was the input to the AD converter? Okay, and it is shown graphically on this slide. So suppose that this input process from -1 to +1 had this Gaussian shape. Of course, if it is proper Gaussian, it is unlimited. It goes to +infinity to the left, to the right, because the Gaussian function is not limited to a certain range. But in this example, let's consider we have a Gaussian function that is properly limited by ±3 sigma, something like that. And we suppose that after this 3 sigma value, this Gaussian is equal to 0. And if I have this kind of constrained Gaussian distribution, what would be the probability of symbol -2? It is the area below this density. So if I integrate this density along this x-axis, I would have this area is equal to the probability of signal being between -1 and -0.6. If I integrate in this range, if I compute this area below this green line, then this area is equal to the probability of input signal being between -0.6 and -0.2. All these can be also derived directly from cumulative distribution function, because this cumulative distribution function, this blue line, is just the integral of this green curve. They are not shown in the this green is not shown in the normalized relationship to this phi, to the CDF. CDF ends up with the value of 1. So the probability that x is less than 1 is 100%. So definitely, signal cannot be lower than -1. Probability, this cumulative probability starts from 0, and this cumulative probability ends up with the value of 1 at this right bound. So the signal cannot be larger than +1. And this blue curve is nothing else but the integral of this green curve. Okay, and it is shown here. This phi x of x is the integral from -infinity to x, fx of x prime dx prime. So I integrate this density from -infinity to value of x, and I get the cumulative distribution for value x. And that is what? That is the probability that x is less x0 inside. Okay. That this value is smaller than x0. So the probability that the signal value is smaller than x0 is nothing else but this integral from -infinity to x0 of this density, and that is nothing else but this CDF. So this is CDF, and this is PDF, probability density function. And now, what I do, I take, if I want to find the probability of density in a range, for example, -0.2 to +0.2, fx of x dx. And that is the probability of observing symbol 0. So probability that I would observe symbol 0 that corresponds to real values from -0.2 to +0.2 is this integral of density between -0.2 and +0.2. But that is again nothing else but the difference of the cumulative density function, cumulative distribution function of +0.2 subtracted CDF of -0.2. So I take this difference of these two values, this one minus this one, and this difference is equal to the area of the below the green curve. Okay? So instead of integrating probability density function from -0.2 to +0.2, I can differentiate the cumulative distribution function at the upper bound minus lower bound, and I get the same value. Okay, that it is equal because due to the definition of the cumulative density function, it is easier way to compute the probability of one class. I simply differentiate what is the CDF at this point minus CDF at this point. Difference of these two values is equal to this shaded area below this PDF function. Now what I have probability for -2, -1, 0, 1, and 2. I have probability for each of the classes. Okay, and now suppose, first of all, that we have the trivial example when this density function is not Gaussian like shown here, but uniform. So all values from -1 to +1 are equally probable. So the density function is then nothing else that it is the, so this is -1, okay, this is +1, and I know that here we have n classes, and each class is delta y. In our example, it was 5 classes, each was 0.4 wide. Okay, so this delta is 0.4, and this n is 5. Okay, n is 5. I have 5 levels, and each level corresponds to a real value that is 0.4 wide. Okay, so the whole range is n times delta. And what is the PDF? The PDF is then 1 over n delta y because this integral must be 1. So it is 1 over the n delta if 1 over n delta if x, not very nice. The density is 1 over n delta if x is element minus 1 plus 1, and 0 otherwise. Okay, that is our density fx of x. So we assume that we have uniform density of values, input values, from value of -1 to value of +1. Okay, so what is the probability then for each of these classes? What would be pi? So what is the p minus 1, p minus 2, p minus 1, p0? So what is the integral of this? It's 1/5. So each probability is 1/5. Why? Because I simply integrate this fx of x in this range. So for example, this p minus 2 would be integral of this fx of x dx from -1 to minus what? 0.6. Minus 0.6. Okay? And I know that this here is, in our example, 1 over 2. 1 over 2, yes. With delta being 0.4 and n being 5. Okay? And then I can extract this value in front. 1 over 2, and I have integral of the dx from -1 to minus 0.6. And that is, of course, 0.4. So this is 0.4 divided by 2, and we have 0.2. That is 1 over 5. So we get the probability of this class being -1 is 1 over 5. Of course, it is the same for any of such classes that are 0.4, right? Because this 0.4 is nothing else but this difference between the upper bound and lower bound of the integral. Okay, now we have the solution that this probability p minus 1 equal to p minus 2 equal to p minus 1 equal to p0 equal to p1 equal to p2 and equal to 1 over 5. So all probabilities are the same, they are just 1/5 in our example. Okay, and now we can compute what is the entropy of such source, and that will be sum of I from 1 to 5, negative sum pi log base 2 of pi, and that is 5 times 1/5 log 2 of 1 over 5, or 5, to be honest, sorry. So it is 1 over probability, that is 5, because probability is 1/5, and now 1 over probability is 5. And this 5 and 5 is cancelled, and I get logarithm base 2 of 5, and that is 2.32 bits. So this is nothing else but this n. How many classes did I have? I had n classes, 5 classes. I have this entropy in this case is logarithm base 2 of n. Since n is 5, then we have this value of 2.32 bits. Okay, so that is the entropy if all classes are equally probable. And what is the distortion? Okay, blah, 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 blah. What is the distortion? Distortion, as we discussed before, so it is nothing else but the expected value of quadratic difference between the ideal and quantized value. And we have shown that this is at the end, it would be for high rate approximation. For high rate approximation, it would be this delta square over 12. But if we have only 5 levels, then we cannot assume that this high rate approximation is valid. And what we have to do, we really have to find the expected value of the squared difference. Okay, and by definition of the expected value, it is nothing else but this function of random variable, so the squared error, multiplied by density of the random function, and integrated over the range of this random function x. Okay, so this is by definition the expected value of square difference x minus x hat, or x quantized squared. So it is this function, I write this function, x minus x hat squared. I multiply this with the probability density function of this function x, that is the random function x. I integrate over the whole range of x, and I get this expected value. That is the definition of expected quadratic error due to quantization. Okay, and since our quantized signal has only discrete set of values, so this x hat is element from, how it is called, xq minus 2. So I have this xq minus 2. I have this x quantized minus 1, and blah, 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 up to x quantized 2 plus 2. So these are possible values for the quantized signal. And for that reason, I can separate this integral into sum of 5 integrals. So I have the range when x corresponds to the first quantized value. This integral can be separated into sum of 5 integrals. First integral, when this x falls into the interval corresponding to xq minus 2. Okay? Second integral, when this I is minus 1. So it falls into the interval for xq minus 1. Blah, blah. So instead of having single integral, I have sum of 5 integrals. Why? Because if I select first of those 5 integrals, then I know that this value, this x hat, is nothing else but this xq minus 2. In concrete example, this first quantized value was minus 0.8. So for all of the values of signal x from minus 1 to minus 0.6, the quantized value was minus 0.8. And that is this value xq minus I, or xqi. This I is equal to minus 2. So I know this value, it is minus 0.8. So for the first integral of those 5, this is constant value. Okay, this is constant value. Okay? So this distortion is then found by summing up individual distortion in each of these 5 integrals. So starting from the first integral, I can replace the original variable. This original variable was x. I can replace this variable x with x prime, and this x prime is shown here. So this x minus delta times I is x prime. So if this is introduced as x prime, then this range is then nothing else from minus 1/2 of the step size to plus 1/2 of the step size. And in this new variable, it is x prime squared dx. Now I have assumed that if the signal has uniform distribution, so this fx of x, this here, is constant. So I can take this fx of x in front of the integral. So I started with these 5 integrals. I have these 5 integrals. But for each of the integrals, this fx of x can be taken in front of the integral because it is constant. It does not depend on x. And that is the form we have here. So this 1 over delta n, that is this fx of x. It is taken out of the integral. And I have sum over 5 intervals, from 1 to 5, from -2 to +2. And in each of the intervals, this integration, what is left in the integral, is this difference, x minus xqi. But this xqi, this value, is nothing else but this index I multiplied by delta. So for example, that is xqi. Okay? For I equal to -2, it was -2 times 0.4, it was -0.8. Okay? So that is this xqi that I have to insert instead of this value x hat for the first interval, for the second interval, and so on. And that is shown here. Where? Here. So that is this delta times I. This delta times I is the quantized value of the signal that falls into this it interval. -2, -1, 0, up to +2. And after this substitution of this variable, so I simply say that this is x prime, this difference, x minus delta I is x prime. Then the range of integration is reduced from this delta I minus 1/2 step to delta I plus half step. After this substitution, it is simply -1/2 step to plus 1/2 step. And now this is a trivial integral. This is x to the power of 3 over 3 between the upper bound delta half minus lower bound minus delta half. And we get this expected result, and that is squared value of the step size divided by 12. So this distortion is valid in two cases: when the rate is high or when the signal density is uniform. So if the input signal density is uniform density, then I would get the distortion that is simply defined by this trivial expression, squared value of the step size divided by 12. Okay? And what is the variance of the input process? So the variance of the input process is, again, the expected square value of the input x. Our expected value of the process is 0 because the process is symmetrical around 0. The density was shown here. So it is symmetrical density around x equal to 0. And due to this symmetry, the expected value of x is 0. Then, in order to find the variance, I simply have to find the expected value of x minus a of x. So that is the variance. That is, by definition, the variance. So I take the random variable, I subtract the expectation of random variable, I square this difference and find the expectation. So that is, by definition, the variance of the random signal. And if this is equal to 0, as it is in our case, then this is reduced to simply expectation of x squared. And this expectation of x squared is, again, by definition, integral of this function x squared multiplied by fx of x dx over all values of x. Again, this is 1 over n delta, this density. It can be taken out of the integral. So I have this 1 over n delta. And I have this integral of x squared dx from minus n delta half to plus n delta half. That is the range of the signal values. So that is the range of signal values. And what I get similar solution as before, but now I have n delta squared over 12. Okay? So the solution is analog to the distortion, but instead of having squared step size, now I have n times step size squared over 12. And now we can finally relate the distortion and rate. Distortion is defined by 10 log 10 of quantization error. That is, okay, sorry. This ratio is the variance of the signal over variance of the quantization error. And that was this d value. So this was n times delta squared over 12. And this was delta squared over 12. And I have, and this is then 10 log 10 of n squared, or 20 log 10 of n in decibels. And at the same time, the entropy was log base 2 of n. So this is the signal to quantization noise ratio, SQNR. Signal to quantization noise ratio is this value 20 log base 10 of n. I will write it once more. SQNR is 20 log 10